test. So first type of questions maybe what is electrochemical biosensor and describe the importance of this technique. So this is the first questions. What is electrochemical biosensor and describe the importance. So first of all, one thing. Okay, so I will ask someone. So please let's discuss with you. Sarfaraz,
Yes, sir. I'm
how
here.
are you, Sarfaraz?
Yes, sir. I'm fine, sir. How are you?
I think good, good, good. So I think you understand, right? Whatever I taught in this class.
Yes,
So,
sir.
so please, can you please tell me what is the electrochemical biosensor? The definition of the biosensor, electrochemical biosensor.
Um, Sir, a biosensor is an is a device which is used to detect some kind of target or biomarkers in the analyte solution
Mhm.
with the help of some receptor or like an
Mhm.
uh, antibodies and everything like this. Yes,
Okay.
sir. So it may be like there are a few types of biosensors that we know, that electrochemical and also you know, and yeah, there are many kind of biosensors I know, electrochemical and all these.
Sure. So
So
I asked the question the electrochemical biosensor, right? So electrochemical biosensor means in this case, you have to you are applying some electrical some input like potential something like this, right? And
yes, sir.
you will get some output like electrical output like current or charge,
Yes,
right?
sir.
So that will be the
Definitely, yes.
electrochemical. So why electrochemical biosensor is more important than any other biosensor?
Because as they are simple and they are very
So
sensitive and
yeah,
accurate. So all
yeah,
these things.
this thing you have to describe. It is very
Yes,
simple,
sir.
it is sensitive, we can easily miniaturize, and it is very cost effective, not expensive, right? Affordable.
Yes, sir.
So these things we have to
They
describe.
are they are kind of the best in the market. Like
Right, right. Easily you can commercialize.
yes, sir.
That thing you have to describe. Okay.
Yes.
Okay. Now how you can calculate the limit of detection of biosensor from a calibration plot. That I think just last class which I repeated. So some of you can answer right now. So who can? And Bhavesh Delta. Datla, sorry. Bhavesh? Hey Bhavesh, are you there?
Yes, sir.
I think you understand what is the limit of detection, right? Yes, last class also I taught you. Hmm?
Yes, sir.
So please read the questions. So how to calculate? So this kind of questions may come. So how to calculate the limit of detection from a biosensor from a calibration plot? So if we provide you with current versus concentration, so tell me the answer.
Hello.
Yeah, please tell
Sir,
me the answer. What is the limit of detection?
so like limit of detection is critical factor means it helps in identifying and quantifying means what is the limit at which limit we will get the amount like the target molecule means how much at what concentration we will be getting the accurate result we wanted. Like for that we have to go for different plot what to say we have to plot the curves for different uh, types of things. Like we have to go for Coulomb calorimeter, and then you have to go for CV also. So in that way we can go. And means first we have to take like for let's take an example of charge versus we have to first go for Coulomb calorimeter, and we will take a time where the maximum charge will be obtained.
Not coulomb, it's chronocoulometry.
Yeah, yeah,
Chronocoulometry.
yeah, chronocoulometer. So in
Mhm.
that we have to fix one time, and we have to not check at what voltage or at what time the maximum charge is coming, and then we have to plot the curve for concentration versus charge, and then that we can know that okay, this limit is coming, and in that way we'll get the detection limit. And same we have to do for voltage versus concentration also.
You can describe only one single technique, not all technique. Maybe you can that in the questions, if you see, I can show you again. The question is how to calculate from current versus concentration, just for example. So then it is kind of chrono amperometry, right? Or maybe cyclic voltammetry, current versus concentration. You can fix maybe only one technique, maybe CV or maybe chrono amperometry CA.
Yes.
But CC case charge versus concentration, right?
Yes, sir.
Okay, but still you can improve the your answer. I think I can ask to Bhuti. Bhuti, are you there? Bhuti Bhushan?
Yes, sir.
Yeah, Bhavesh, your question answer is fine, but still you should improve the answer. Huh? So Bhuti, please can you please answer this
Yes.
question?
Okay.
Bhuti, can you please answer this question?
Yes, sir.
Tell me.
Sir, you are asking to answer the questions, the previous question.
Yeah, the how to calculate the limit of detection.
Sir, limit of detection is the minimum amount of the analyte that we can detect with the help of the biosensor.
Right. These things, yeah, these things you all have to mention the minimum amount of concentration you can detect.
Yes,
Okay.
sir.
The next again.
Then in the graph, we have to get the standard calibration curve
Mhm.
of the current and the concentration.
Mhm.
Uh, then at the zero concentration value, we have to multiply it with 3,
Mhm.
and with the help of that, we can have the limit of detection.
Mhm. So then you have to maybe you have to plot all the concentration curve.
Yes, sir, yes, all the
All
concentration
the
curve along with
concentration,
it.
then you have to intersect, or maybe the lowest
Yes.
constant that will merge with your 3 standard deviation line. That will be your limit of detection, right?
Yes, yes, sir, yes, sir.
Okay, good. I think you understand this one. I think who you can read it again. So now the next question is how to modify the electrode surface with gold nanoparticle. Let's answer this one first. How to modify the electrode surface with gold nanoparticle? Who can answer? Can you raise your hand? Anyone? How you can modify your surface with gold nanoparticle? I can't see. Who can answer? Bobis, you already answer. I know you understand. Anyone else who can answer how you can modify your surface with gold nanoparticle? Anyone except Bhavesh? Anyone? And Bhupendra also answered. Sorry, Vibhuti Bhushan answered. Anyone? No? Okay. Tamiyan, this Sant, right?
Yes, sir.
So what is spelling? Can you please tell me your name?
Dushyant
Tami-
Kumar, sir.
Dushyanth Kumar.
It's
No, no,
Tamil.
first
Yeah, Dushyant Kumar is my first name, sir. Tamil is my surname.
okay, because I can see first one is the Tamiyan. Okay, Dushyanth Kumar is the first name. Okay, fine.
Yes, sir.
Okay. So can you please tell me now then how we can modify the surface with gold nanoparticle?
Yes, sir. After putting the after we put the sample, like whatever it may be, blood or anything, we will insert this gold nanoparticle. Sorry, after putting the blood, we'll wash it, and after washing, we'll put the secondary antibody, that is a gold one, and this gold, after some we will stay for some time and we'll clean it, and then it will detect how to immobilize primary antibody. Yeah,
Yeah.
that's what I'm saying, sir. How
That
to
is fine.
we remove.
Yeah,
Hello.
that is actually for detection. Means that is secondary antibody. That is a detection procedure. I asked how to modify the electrode surface. Means just without antibody, just surface, electrode surface. No antibody, just surface. How you can modify the surface with gold nanoparticles? Hmm. How?
Sir, sir, I remember it, but like we'll put in some solution and we'll apply electricity on both sides,
Right.
and
Right. Can
the
you?
gold inside the solution will come and will attach into on the surface itself. I hope it's correct, sir.
I think looks good, but not fully correct. Okay, let's see the another one. But actually, the first answer was fully wrong. That I actually wanted to ask to how to modify only the surface, gold electron, no antibody. Huh? But second one close to the answer. Okay, let's ask Shomo Vishwas. Shomo?
Yes, sir. I think we have to select a salt of gold, and then we have to reduce it to from its higher oxidation state to lower oxidation state, and this is the main process by reduction of a salt of gold to its zero state oxidation state, and then I think it will be, yeah, that is how the gold particles are created, nanoparticles are created, and then I think it needs to be deposited on the surface of the transducer to uh,
Yeah.
increase.
Yeah, this is one technique. This is right. This is one technique. There is okay, it's fine. There is some another technique also there. I think someone else can answer here. So, who can answer? That is fine. Anyone?
Sir,
Uh,
electrodeposition we can use.
yeah, the electrodeposition we can use. We can apply some potential.
And we need some chemical like Ha4Cl4 like chemical too for the
Yeah, so you can use HACl4, that
So
is
we
fluoroauric
can
acid.
clean with the ethanol for the 10 minutes,
Ha.
and
So
then
you can,
hydrogen peroxide we can also use after the subsequent washing.
yeah, that is actually full possible. If you want to say like this also, so what you can say means you can immobilize the surface first, right? I mean you can clean the surface first, and then so you can do. So what you can say that if there is any impurity there, that can be removed by that I mentioned, like hydrogen peroxide, ammonium hydroxide, and water mixture, right? That is 1:5 mixture. Then you can clean the surface. That's fine. So you can remove all the contaminant and clean. Then in this electrode surface, you have to use a solution. So which solution? Like if you want to modify the gold, then you have to use a gold salt solution, like this one, chloroauric acid. If you want to modify platinum, then you have to use chloroplatinic acid, this salt. This is the salt. So you have to dissolve it in the solution. Then you have to apply in this electrode some negative potential. Suppose around 0.3 volt. This much potential you have to apply. In this negative potential, so what will happen? So like higher oxidation state gold, it will deposited as a lower oxidation state AU0. Now like whole like nanoparticles, it will be deposited on the surface. Now you can wash the surface, then you will get the nanoparticle coated surface. Clear? That is one technique. Another technique, you can use some chemical like reducing agent. Some reducing agent. What kind of reducing agent? Like sodium borohydride, right? I told. If you mixed this sodium borohydride with chloroauric acid, then you will get a mixture of solution. That is called gold nanoparticle mixture. So that one you can drop on the surface, like drop casting. You can drop the surface and keep it for half an hour, something like this, and you can wash the surface. Then you will get some nanoparticle coated electrode. Clear?
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay, good. Then go to the next
Sir,
question.
sir, I have a question.
Tell
Sir,
me.
I heard about Milky water, sir. Is it also used for washing?
Well, yeah, Milky water means just for this electrode, like there is no antibody, nothing, that you can wash by Milky water or DI water. That is very purified water. There is no contaminant. But generally, if your surface coated by some biological stuff like antibody or protein, something like this, then don't use the only simple Milky water. They can damage your surface and they can wash the protein also. It is better to use some buffer like some contain some electrolyte like sodium chloride, some or sodium hydrogen phosphate or something like salt should be there. So it looks like real with your blood sample. Your blood samples contain lots of salt and pH around 7.4. So similar pH and similar electrolyte if you can use, similar like just like a buffer, phosphate buffer saline. It is similar like your blood pH and some salt also contain your blood. So it looks similar. So your protein also will be very much stable in that pH. So that's why instead of use only milky water, we are using buffer. But if your surface there is no biological molecule, no antibody, you are free to use any kind of milky water also. Okay.
Sir, BSA can also be used, sir.
Yeah, BSA can use, but when you are going to minimize your non-specific binding that time.
Okay, sir.
Okay. That time. Okay, good. Then go to the next questions. How to immobilize primary antibody on gold nanoparticle modified surface? So, okay, let's come here. Means your surface now. Let's enter one thing. So now what I am asking, your surface now. This is your electrode surface, electrode or transducer. This surface already coated nanoparticle, right? Now, how you will immobilize a primary antibody, antibody 1, on your surface? Tell me, how you can immobilize primary antibody on the gold electrode, that is, then sorry, the gold nanoparticle modified your electrode surface? How? Maybe I can ask someone. Can you raise your hand? Who can tell me this answer? Brotin, can you answer these questions?
Yes, sure, sir. So, primary antibody can be immobilized by different methods. We can use COH NH2 specific binding, or NH2 COH specific binding, or else gold nanoparticle has a inert property to interact with thiol group that are normally present on antibody because of these disulfide bonds. So gold nanoparticles, before coating those gold nanoparticles, they can be normally concentrated acid with high heat can be used, so that COH group is present on the gold surface. Then the primary antibody is uh, uh, is coated on the gold surface, or else because of the presence of thiol group on the primary antibody, the interaction can take place.
No, so for actually thiol group it's present, but that is a dimer like thing. So there is one way we have to actually basically I mean you have to bring this thiol group here by some conjugation procedure. So here actually some conjugation procedure you have to follow. Then you have to make this a sulfur group on the surface. Sorry, on the antibodies end. You have to make a thiol. I mean some you can say this open thiol group. You can make it by some conjugation procedure. That conjugation procedure maybe it is available already, but that is not much complicated. If you want, you can read also. The thiol group can be easily modified on the antibody. Now, if you this antibody that is already thiol modified, if you drop it on the gold nanoparticle modified surface, then it will be easily bind on the surface, because thiol and gold, they have inherent very good affinity. So this is a very good answer, first of all. And second answer you can make, yeah, definitely this amine group or carboxyl group formation you can do. That's I taught you already, like EDC NHS method. These things you can follow. Right?
Yes, yes, sir.
So
Okay.
can we use that avidin and biotin related stuff for this thing?
So you can
So
Bhupendra, right?
Bhupendra, yes, sir.
Uh, you can use this one. Just come here. Yeah. No, not this one. Yeah. See, so if you want to use epidin biotin stuff, so still it is a method. So you are also correct. You can use, if there is gold nanoparticle, so you can modify here some epidin, right, on the gold nanoparticle.
Yes,
Then
sir. Yes,
then
sir.
you can drop like biotin-related antibody, right?
Yes, sir.
So what will happen? So why we need? So instead of gold also you can use only these two procedure, right? But gold nanoparticle basically will help you to increase the conductivity, right? Conductivity. So that actually will help you to
But
get high signal to background ratio. Yeah, tell
sorry,
me.
but if you use Evidin directly above it, what is the purpose of putting gold prior before it, sir?
See, so this electrode, like if it is an electrode just like a carbon electrode, right? So it has a very less conductivity, right? So very less conductivity. So the electron transfer rate will be very, very slow. So somehow you have to increase the electron transfer rate. Otherwise, when you put the lots of protein on the surface, so electron conductivity again is decreasing, right? So means if you want to get the high signal, so your conductivity of the electrode surface also at least somewhat you should have. So if it is fully, non-conductive surface, if it become, then you cannot make a very good biosensor. It is a good question. So who asked this one? It's very good one. Okay, now clear for you? Just think. If it is clear, then otherwise I can repeat. Bora Arvind, right? Arvind,
Yes, sir.
is it clear?
So can you repeat once more, sir?
Yes, sir.
Okay, here I can repeat again. This is very good question.
Sir?
So this kind of question always will come. Why we are modifying gold on this surface? Instead of gold, we can do this one, right? Why we are modifying gold? See, if there is no gold nanoparticle, like here the ABD, right? The biodynamic antibody. See, lots of protein coming on the surface, right? So this is your sensor, but your sensor conductivity is slowly decreased. So electron transfer rate very slow. So basically, you will get very low signal. So somehow you have to increase the conductivity so the electron can flow easily on the surface. So that you can do by modifying the surface with nanoparticle, that is gold. It will help to transfer the electron very fast. Then only you can get increase the signal, and also you can minimize the background that I told. There is so many way you can minimize the background, like using the BSA to minimize. You can non-specific binding you can avoid. Like this, you can minimize the background and you will get the high signal, and signal to background ratio will be much better. Yeah, ask me. Any question? Hello, do you have any more question?
No, sir.
No. Let's go the next question.
No,
Let's go
sir.
next. So describe the signal to background ratio in the below electrochemical. So see, this one actually I did teach you, but I can see, just leave it the sentence here. So this is a biosensor, right? So I am asking you which here which one signal and which one background. Can you tell me anyone? Yes, this is a biosensor. Just think about this is a biosensor. Tell me which one signal, which one background. Anyone?
So the right one is a background and the left one is the signal.
Uh, yeah, somewhat correct. But who answered this one? Shivam, right?
Dushyant, sir, Dushyant.
This one, right? Okay. Okay. Uh, here, here, yeah. See here, this one. If target
What
present, then only the signal come, right?
sir,
So
what was the question? Can you repeat once more?
now in this, so suppose this is a biosensor,
Yes.
right? This is a biosensor, and here we are using lots of chemical. So this chemical compound name already I put here. So now think about which one signal, which one background. So this one tell that in this case, left one is the signal, right one background. But you but it is partially correct, not fully correct. Full answer will be if there is no target, then it is signal, right? So if there is no target, then ALP will not be there, right? This is the ALP conjugated some antibody. So this antibody will not present. So this antibody will, if not present, then this compound cannot react with this ALP, right? Then this compound actually form this compound. So if ALP not there, then this compound formation will not be there. So basically, in the signal case, so this compound reaction will be absent, right? This one. Can you see my cursor? Right?
Yes, sir.
Yes.
So
Yes, sir.
this compound will not be formed if target not present, right? So basically, this one will be so target signal will be target when it is the signal, then this is the full reaction. It is caused by the signal, and if there is no target, if it is background, then absent of this, it is the background. Clear? So if the target, then only this reaction possible, right? And this is generating. So this chemical, TCP, this chemical, and RUNH3, this chemical can be there always. So this Ru NH3 whole 6 TCP and NH2 OPO3, and this one can be present for 0. So only target case, what is the difference? This reaction will be stopped. That is the ALP related reaction. I mean only this one forming, this middle one. So middle one will be stopped for the target case. So except this, it is the background, and with this, it is the signal. Right? Clear?
Sir, this reaction, RU related reaction, is actually our signal.
Yeah, this full reaction is related to the signal, because see, target present, ALP present. ALP, it is a secondary antibody, right? Secondary antibody conjugated this ALP. ALP is a kind of enzyme. Just think about this is the enzyme. So this enzyme helping this reaction to this reaction. It's only this middle reaction. But
So I am talking separately about the signal and background. So you said that if we don't have the signal, then this reaction NH2 whole OH to P2Q, to be more specific, will not take place.
will not take place. Yeah.
So
Yeah.
so our aim is to just have the signal, then we will get this full reaction.
Right. So our aim to create the whole reaction. If this in between this one stop, then this full reaction will be stopped. This reaction will not be possible. So if see, so there is stairs, right? This is kind of stairs. So you're breaking one step, then this reaction actually becomes stop. So if the target there, then this step actually adding the full stairs, then you can easily reach to the reach the end of this your path, something like this. So signal actually, I mean the ALP actually helping this step, this reaction. So then the full stair actually connected. Then you can easily enter to the end of your path, something like this. So if there is no ALP, then you are breaking your one step. So this reaction cannot possible. Clear now?
Sir, these violet colors are compounds are these are already present, na? Like this
Yeah.
R1P and R2. These all three are already present in the solution.
No,
So, sir,
PQ
yes,
will
sir.
not be present. PQ and Q will be generated during
Yes,
the
sir.
reaction. O1, R1, they will be present on your sensor chip. This reagent will be present.
Sir,
Actually,
O1 will be present or R1, because R1 is forming
right. I'm going to
O1.
say. So R2 will be present and
Yes.
R1 will be present. So
Yes,
these
sir,
two chemical, R1 and R2 will be present in your sensor chip. They will take part in the reaction, and this one will be present in your chip. This one.
Sir,
Can you see my cursor? This
yes,
one.
sir.
This chemical will be present in your chip. Then full reaction will be take place. If the target present, then ALP come and it will help you to bring this step, and it will be connected to all the reaction. So if there is no target, so this step will be stopped. Then full reaction will be stopped. Clear?
Sir, yes, sir. So noise is there because of some kind of non-specific binding. So what kind of non-specific binding can be there in this case without present of ALP?
Very good things. So you are surprised, right?
Yes, sir.
I think surprised you understand the problem now. I am happy that you understand this one. Very good question. See now here. So this is the full reaction for the specific binding, right? Now, if what is non-specific binding? If this secondary antibody conjugated ALP can bind except this place, they can bind also in the surface, right? This surface here. Can you see my cursor here? So if you bind here, that is non-specific binding. So specific one, it should antigen antibody binding. That is specific one. But if they can bind on the evidence surface, then it is non-specific. Suppose you don't have target, right? So this ALP should not bind here, this specific side. But if they bind the non-specific side, but then what will happen? Some ALP, if they present on the surface, then that ALP can convert this compound to this compound, right? This P. Then this P can take place in this reaction. Then whole this reaction will be take place. Then your background will be means your it will behave as a signal. Then means some current can be generated. So it means although you don't have target in your sample, but still you are getting some current. So it is caused the noise, means increasing the background. That That's why non-specific binding cause the increasing background. Clear now, Sarfaraj?
Yes, sir. So, sir, if there's nah, if there is no biomarkers, so there will be non-specific bindings. Okay, so like if there is some biomarkers, so there will be no non-specific bindings. So
No, no,
like
like
how?
this. Not like this. See, so if there is biomarker, so that's why if you want to develop a very good sensor, so what you have to do, you have to make a surface, you have to wash your surface by like the BSA or something like surfactant that will be immobilized, that will be I mean occupied by this small gap and or the non-specific side, so they will occupy. So what will happen when the ALP because antibody will come, so they will not occupy anything on the surface. So like this way, you have to minimize the non-specific binding. If you are not able to minimize the non-specific binding, then your sensor will not be very good sensor. Yeah, this is the first thing. When you will develop a sensor, this thing you have to keep in mind. You have to anyhow you have to decrease the non-basic binding. So how you will decrease that? You have to put lots of BSA or some surfactant, something way. So you have to think about, you have to optimize the concentration of the BSA, something like this. That is the first criteria. So if you have target, still you will get some non-basic binding, maybe, right? In the target, it can be bind here, and again it can be bind here. See my cursor, it can be bind here also. So it means maybe your target concentration 1 nanogram. I mean 1 nanogram if it is proportional to one target. But if some non-basic binding, so one ALP here and one ALP can bind on the surface, then it will be corresponds to a 2 nanogram target. But you have only 1 nanogram. So it means non-specific binding actually increasing your background. So you are thinking your target concentration 2 nanogram, but it is not. It is actually you have 1 nanogram, something like this. So if you can minimize non-specific binding, then you will get the correct current or correct charge. And in the case of zero case, so this ALP should not bind here, and you should not get this semi cursor, this product. But if there is some non-specific binding, then ALP can bind on the surface, means ALP, then this reaction can take place. So you will get, although you are thinking in your sample there is no target, but still you are getting something, then it will mislead you. So maybe you can think some still target there. Okay, Sarfraz.
Okay, sir, got it.
So this is the first criteria. You have to minimize non-specific binding. Yeah, tell me.
Sir, so the final answer is like which signal we have to show the target and the ALP signal giving to that middle one. And the background means excluding both.
Except this middle one, this is the background.
And target, it's background.
And except this is the background. And with this, it is the signal. And except this means you will not have target then. This one will be absent.
Yes, sir.
Right?
And that will be background.
That will be background. Right.
Thank you, sir.
Sir. So what is this T-shape?
Oh, this is actually just, I didn't teach you this one. It will come, but just for an example I kept. T-shape, this is kind of reducing agent. It's full from, if you search in the Google, so I can search on for you. This is a very big name. So I put that, so just T-shape. Just I'll show you. Here, T-shape, TCEP. So T-shape, see, there, see, reducing agent. So this is the name, is a very big compound. This is kind of a good reducing agent. This full name is tris 2 carboxyethyl phosphine. Okay, this is the full form of the T-cell. Clear?
Yes.
Yeah, this is the reducing agent one. It will help to reduce. Okay, the next question now. Right?
Sir, I have a doubt, sir.
Tell me. No problem.
Sir, whenever the secondary antibody with the enzymes, alkaline phosphate will be present, so these reactions will take place.
Right.
Irrespective of the presence of primary antibody or not. If the secondary antibody bind to the primary antibody, then it will be the specific binding and is the signal.
No. If it is bind with the secondary antibody, then it is also not a good sensor. So it should bind with the target. It should not bind with the antibody.
Yes, a target. Right. And if the secondary antibody with the enzymes bind to the surface, then we'll call it it's a non-specific and background.
And background, right.
So I'm just trying to understand the steps. If the ALP with the secondary antibody will be present, then P is converted into Q, and at the same time R2 is converted into O2 in the right hand side.
R2 convert to the O2, right.
And at the same time, R1 is converted into Nini. O1 is converted into R1, and then R1 is converted again into O1 and giving rise to electron at the same time.
As I said, this is kind of stairs happen, kind of the cyclic reaction. So this PQ actually connecting these two reactions. How see? Actually here we are applying some potential, then R1 convert to the O1, and then O1 convert to R1 by the help of this P. And this P actually generated from this compound. You can see my cursor. If ALP present, then this convert to this P. In the presence of P, this O1 convert to the R1. If there is no P, then this one cannot be here. This kind of cyclic reaction. So one step actually you are actually disconnecting this reaction if you are removing this P. See, if there is no P, then this cannot be converted to here. Clear?
Sir, yes, if there is non-specific binding, so there is ALP. So we will get P eventually. So this reaction
that's the increasing current. That's the increasing current. You will get P. But yes, see, non-specific case, you will get very, very low amount ALP. But specific case, see, there is here I saw just for example only one antibody, but there is thousands of antibody on the surface, right? So you will get lots of antibody that conjugated ALP. You will get if target present. So in this case, if you have non-specific binding very, very low, then you can actually minimize this one, because compared to the non-specific binding, your specific binding too much. Maybe you have non-specific binding 2 or 3 ALP, but you have specific binding almost 1000. So if you compare 1000 with the 2 or 3 ALP on surface, so you can avoid that one. That is the thing. But that's why background you will not get always zero. Somewhat current will be there, because you 100% you cannot avoid non-specific binding. Some ALP will be there on the surface. Some little bit amount will be there. You cannot avoid fully. I mean, 100% non-specific cannot avoid.
Excuse me, sir.
Yeah.
So you mean to say that when the target is not present, could you please go back to the picture?
Which one?
Yeah.
Yeah.
Yeah. So when the target is not present, the middle reaction, which is P2Q, won't happen, right?
Right.
But the reaction R2 to O2 and R1 to O1 will happen in spite of it being not present, like, right?
Yeah, see here, actually, we are actually applying, this is the electrochemical sensor, right? We are applying from the outside here, just see my cursor. From here, we are applying some potential. In this case, R1 actually convert to the O1. This one will only help. R1, so reaction will start from here, just from R1. So in your sample, R1 will be there. So R1 will be converted to the O1. Then if P present, then O1 will be converted to the R1 again, and P will be converted to the Q, and this Q will be converted to the P again by the help of R2, because R2 the reducing agent, it will help Q to P, and R2 itself will be converted to the O2. So this kind of cyclic reaction.
Okay, so TCP is present in the solution, right?
TCP will be present in the solution, and R1 will be present in the solution.
Okay, so but then when you're saying that the reaction O1 to R1 won't happen in the absence of P, which is ALP, then if TCP is a reducing agent, then the reduction should happen, no? Because that reaction from O1 to R1 is a reduction. Reaction.
It is also
so
kind
why
of.
does it not happen?
That is also very good question. I am going to teach you next class, not immediately. So that is actually, I'm impressed that you asked these questions. Who are you? What is your name?
Sakshi.
Sakshi Raj. What is your background, Sakshi?
So electrical engineering.
Electrical engineering. I am happy that from the electrical engineering background you are asking these questions. Actually, I am going to teach this one after next class. See, that is very good question. See, this R2, this one reducing agent. This one can react this compound, ruthenium compound, right? So this is also can cause the ear background basically, right? Sakshi, that's you are asking. This T
Yes,
shape
sir.
can react with this. So although P and Q not there, but still this T shape can react with this compound and it can cause background. That's why this is the main criteria of the selection of the reagent. So after next class, actually, I'm going to teach you how you will choose this kind of the chemical. During that time, I will describe. But as you ask this one, I'm going to tell you. So you have to choose the reagent such a way so that this reagent and this reagent reaction rate should be very low or almost nil. So we already checked that ruthenium and T-shape, this reaction, actually you cannot avoid, as I said, but still very slow, very slow. That's why your background will be increased, but not that much. Okay, Shakshi, this T-shape
Okay.
and this reaction very slow. But if you choose something like X, some chemical here, but if T-shape react with this chemical very fast, then your background will be very high. You cannot get a ultra sensitive biosensor. So when you will choose the chemical, as I said, I will and describe this one very descriptive way again, not today. So this reagent and this reagent reaction should be slow or no reaction. Okay.
Okay, sir.
Okay. Thank you, Sakshi. Very good question. Thank you. Okay. So next
Okay,
question.
sir.
Go the next question. What is the basic difference between chronoamperometry and chronocoulometry? Tell me. Who can answer this one?
So one measures current and the other measures charge with time.
Okay. And what is the similarity there?
Similarities are the current and charge are related, so I can be written as Q into T. So, according to me, one of the problem in chloroamperometry is that the signal is a bit more noisy. Things overlap at various concentrations. So, but in the chlorocoulometry, things are more linear because charge is always increasing with time, and there is no possible cause for intersection of various signals. So that's, I think, a reason why at times coulometry is preferred over amperometry.
Yeah, but no, that is fine. That chronocoulometry case, we are getting lots of very good difference also. Then
Sir,
chronoamperometry.
sir, for the main point of similarity is that, yeah, here it is written that caused by the potential step, which I was going
Good.
to say this thing.
Yeah, that is the similarity. In both cases, we are applying certain potential. That is the
Yes,
similarity.
sir. Yes.
And one case we are getting current, and another case we are getting charge. And these things you have to keep in mind. This diagram, chronocoulometry, this is the technique name, and this diagram is called
Gram.
chronoculogram. Right. These things you have to keep in mind. I think very good discussion today. I think it will help you to answer your all the questions during the class test. Now the next questions. Why do the RCT value increase in the electrochemical impedance biosensor and describe with a schematic illustration? So tell me, first tell me the definition of the RCT. So you know the RCT, right? RCT means charge transfer. What is this? RCT, charge transfer
Resistance.
resistance.
Resistance of charge.
So why RCT value increases with increasing the target concentration?
So with the increase in the biological entity on the electrode surface, the RCT was increasing.
Yeah. So you have to tell this within this schematic diagram. So when there is no biological entity here, then the electron can be transferred easily. So you are getting very low RCT, right? So when you are increasing the biological stuff, I mean increasing. So basically you are decreasing the electron transfer rate, right? That's why you are getting higher and higher RCT value. So here the full example, like this way you can show some schematic diagram. Or here also, yeah, it is full. Something like if you increase the concentration, you can see here like 1, 2, 3, 4. Like if you increase and increase, then you will get higher and higher and higher the impedance. And so RCT value slowly increase. So then you can plot a calibration curve like this way. Like here RCT value in the y-axis, and x-axis you can put the concentration of your target. Then in the similar way, like 3 times standard deviation for all the concentration and this. So you can see they are not the straight line, but you can put a straight line by using few more points using the here. Intersect will be your limit of detection. Okay. Now can go to.
Sir, with the help of the EIS, finally in the instrument we'll get the RCT value, no?
Yeah, so RCT value actually will help you. In the RCT value you will get that semicircle area. So
This is correlated with the impedance.
Yeah, so that one actually correlated with the impedance that you will get from the impedance, and that will help you how much biological molecule on your surface.
Okay, sir.
Sir,
one more doubt. Sir, what is the double layer? Means the positive, if the electrode is negatively charged and positively charged ions will come, and this is called the double layer.
Yeah, see, I can write I can draw a picture maybe here. Right. See, suppose your electrode surface you are applying here a negative potential. Suppose so your surface negative. So your solution. See, this is your solution, right? Solution. So by electrical biosensor, you should have some solution. It is not the solid surface, right? You should have some sample, like liquid sample. So your sample contains suppose sodium chloride, like Na plus Cl minus. So in this case, what will happen? It is negatively charged, then positively charged sodium ion will be there. Lots of sodium ion will be there, right? Positively charged sodium ion will be there. And then see your water molecule, that is your thinking. So this is also actually surrounded by lots of sodium and chlorine ion, right? So there the negative ion also will come here, close to here. So what will it see in your if you see the microscope, if you think about the microscopic, I mean very close to the surface, there will be the positively charged ion and negatively charged another ion, like anion also will be there. So this is like this, one will be the positive and the negative, some layer will form. So this layer not, see, only sodium plus ion you cannot get in the solution. Actually in the water molecule, it will contain lots of, like, see, this is the negatively charged and O is the negatively charged, right? Hydrogen is the positively charged, delta plus and delta minus and delta plus. So one water molecule can be surrounded by the chlorine ion. This is like a spherical. Oh, no, why you can think like this way. Chlorine ion, it can be surrounded by the water molecule like this way. So it is negatively ion, so positively ion hydrogen will be here. So hydrogen will be close to the chlorine. Hydrogen will be close to the chlorine like this way. So these all ion, positive charge ion and negative charge ion, they will be close to the surface. If it is negatively charged, the positive charge ion will be close to the surface. So like this way, you will get some layer, positively charged layer, negatively charged layer you will get on the surface, very close to the surface. So this is called the double layer. Clear?
Yes, sir.
So this is something. So I think this is very common for any kind of the ionic solution case, and if your surface is charged. Okay, so go to the next questions. What is the basic principle? As a washing free, actually, I didn't teach you much way. I suppose this one I will teach you on Monday. Do you have any exam on Monday? Your gate exam. I think that is the Sunday and Monday morning you will be finished. So you will be free on Monday evening, right? So Monday evening also I will discuss question again, and then the Wednesday you can sit for your exam. Wednesday. Okay, so leave it the 7th part. This one I will teach you then on Monday. 8th is what is non-specific binding of the biosensor that I taught you already. How can we eliminate the non-specific binding? So how we can eliminate
by using BSA?
BSA, right.
Washing with BSA detergent.
Washing with BSA or surfactant.
Or detergent.
Sir, hello.
Yes, sir. Yeah, tell me.
Sir, I have one answer. I don't know whether it's correct for non-specific binding. How we eliminate? Can I answer? Hello.
Yeah, please tell me.
Sir, can we use the opposite like non-polar to polar? Like if you're using polar secondary antibody, we will use non-polar this surface. Then it won't attack or it won't stick.
This one, that is your answer is right and correct. I will encourage your answer. Yeah, this kind of thing if it slowly come in your mind. Polarity, non-polarity, what kind of chemical, what concentration you can use. I say if you use the high concentration of secondary antibody, right, you will get lots of secondary antibody on the surface. So somewhat they can be conjugated. So you have to optimize the secondary antibody concentration, right? And right, this one.
Yes, sir. Yes, sir.
So there is so many optimization process also. So yeah, you have to think about the polarity also. If you can use some totally neutral something, so that there is no binding force on the surface, right? That also may come. That may come, and you can think about. And we have to check actually that experimental value is really happen or not. You have to optimize the concentration, and also you have to optimize also the electrolyte concentration, and also you have to optimize the primary antibody concentration. See, if your surface lots of primary antibody, so somehow it can affect on the non-specific binding also. So lots of things, all the steps we need to optimize actually when we will develop our biosensor in our lab. That actually I am doing in our lab. We are developing the biosensor. Actually sometimes we don't know which step actually affecting. We are getting lots of noise background. So then part by part all the steps we are checking, and finally we are deciding, yeah, this way only we can design a biosensor. So literally or writing in the exam book exam paper also we can design many way our biosensor, but practically they will not exist in the lab. Why? Because of this kind of background noise, too much background. Whatever we are thinking, actually, theoretically they are correct, but practically when we are checking in our lab, so we are getting lots of background. That's why we cannot develop all our idea in the lab. So we have to optimize. If we succeed to optimize all the steps, then you are okay to go for with this sensor and you can commercialize. Okay, this one very good question. Answer also.
Okay, sir.
That will be true. Nice. Okay, so that things actually I bought for you. Now I want to ask you from your side. Do you have any questions? Please ask me.
No, sir.
Sir, sir.
Tell me.
Sir, can you go to that question paper once? That diagram.
Which one?
This one, fourth one. Signal to background. So this non-specific binding is it also a reason for this background noise? That means you are telling that whenever there is no biomarker is present, that means without this PQ reaction, it is called something like background noise. Something you said like that, no, sir?
Yeah. So this is a Nobel case. Nobel case. Background means this is the Nobel case that P should not be there, and if there is a non-specific binding, then somewhat P will be generated. So that's why we are thinking actually this is the background, but your background actually increasing because some ALP actually binding with your surface.
Yes.
So you have to consider that one background, right? You cannot avoid it. So that's then you have to think about this is your background. But
so, other than this, what else can be some other background like impurities, or only this is the reason for background, or are there some other reasons for the background?
No, that's just I think Sakshi asked that questions. And that is the nice question I told you that this reagent we have to select a better way we have to select. So the starting reagent we are thinking these R2 and R1, right? So they should not react actually. If they react, then your background will be increased. So this is the very important step, selecting the reagent. That I will teach you. Don't worry. I will teach you in next class. That will come a little bit late. Let's learn this all the basic things. Then I will come how to select the reagent.
Yes.
Clear? Very good. Anyone? Any questions?
So won't that increase the cost? So won't that increase the cost?
Sorry?
Won't that increase the cost?
Reagent can increase your cost.
If
Yeah,
we increase this percent,
if you use so many reagent, it can increase the cost. But you know, as I said you from the beginning, see our antibody was very highly expensive. Our reagent also highly expensive. Suppose your 1 gram reagent you are buying like I think 50,000 rupees 1 gram, right? But from the 1 gram reagent you can prepare maybe 10,000 biosensor. Just think about 10,000 biosensor. How we can make? Because we need only 1 microgram reagent. Very small quantity we need for one chip. That's why when you will prepare your biosensor chip in a bulk amount, automatically your price will go down, means will decrease. Clear?
so but we have to stay informed about the competition, right?
Sorry, tell me again, I cannot hear you.
Like they those who license the technology don't tell us what they have done in their technology. So if we
No,
use that,
means if you
so
want to develop some like patent something like this, you will not disclose your idea and the technology, right?
yes,
Yeah, that's fine. I mean, as a when you are going for a startup or something like this at the beginning, you cannot say. You can. That's why we are asking. See, for one sensor development, we are asking almost 20 lakh rupees. Why we are asking that much money? Because for generating a simple chip, we are asking 20 lakh money. Is it like the one chip for 20 lakh? No. We are developing the idea. We are developing the technology. So after that, the chip will be only 100 rupees.
so it's the cost of trial and error.
Yeah, definitely. See, that's why I'm asking. We have to go so many optimization steps. We are thinking so many way our biosensor. That is, that can be exist in the pen and paper. But when we come to the our lab, so many problems we have to face. So how we can avoid? We have to optimize all the steps. We have to work lots of work. You have to do. Then you can think, yeah. Then this idea exists and this idea is not exist. So you can go this one for commercialization and that idea cannot go. So you have to decide in lab finally. But your all idea is okay. But when you come to lab, so many background because of that, because of the other reason, some idea you have to eliminate.
Sir, hello.
Okay.
So like we are going for different types of bioimmunization of gold or platinum or so why not we are going with carbon based advanced biosensors like CNT etc.
Yeah, we are doing carbon based. That's why I will one day I will arrange some presentation and I will ask you to read some journal. I will teach you how to read the journal papers. You will see there are lots of carbon based, but carbon case it is one difficulty is that get the conductivity. So in this case, how we can increase the conductivity? As I told, we can increase some carbon-based nanomaterial like graphene oxide, reduced graphene oxide, carbon nanotube. They can enhance the conductivity on the surface. You can use freely. You can use.
Sir, in that means if we use carbon based biosensors then the cost of production or everything will be going down or not?
Yeah, see, carbon-based biosensor it is better approach also I can say because in this case the interference effect very low. That I will teach you that point still I didn't cover. If you want to use the carbon selection of the uh, transducer, electrode material, which one is the best, which one not. That point also I didn't come yet. That also I will teach you one day. How we'll select the material of the electrode. That time I will cover everything. But I am saying your question answer is this that carbon-based material is very good because in this case interference effect. What is the interference? Means our real sample contain lots of other reagent, so they can oxidize also on the surface. You will get lots of background, so that you can avoid by using some carbon-based material like reduced graphene oxide, graphene, or carbon nanotube, something like this. You can use them.
Okay, sir.
Okay, very good. Any more questions?
So
sir.
Tell me.
Sir, I have a doubt, sir. So
Hmm.
earlier I have asked this question, sir, in like the previous biosensor, that we are using the primary secondary antibodies, and finally we get some electrons, and with that conductivity we get some current, and we can say this amount of concentration of analyte is present. But in EIS case, we have using some uh, redox coupled reagents to get the electrons. So I want to ask you, sir, what will be the instrumentations behind the sensors, wash-free sensors, sir? So in the first case, you have shown the primary, secondary antibodies and particles, gold particles, and the step by step. But in the second case, EIS, so what will be the, sir, arrangement, and what is the relation between the electrons generated from the redox couple reagents with the targets and our analytes, sir?
See, as I mentioned, it is as I said, this is the wash free, but again I said the wash free technique I will teach you again. So this is the wash free because at the beginning, so in your hand, I mean user, they will get this up to here, this step, right? Up to here they will get. So that's why up to here. Then no, sorry, not here. Up to here. This is your final step, right? After BSA modification. So this is the user, they will get it. So what you will do? You will just drop your sample, and wait for a few minutes because you need for binding of the target on this surface, right? And you can apply here impedance. And impedance case, you will be provided one test tube, one sample tube. It will contain like Fe3 and Fe2. They can be easily converted. So they will release one electron. That electron, how fast they can go through this electrode surface, that will measure by impedance instrument. So this electron generated by this reaction is fixed. So this reaction always happen here in the bulk chamber. This reaction happen. So if this electron can easily flow, then you will get low impedance. But because of the protein, if they bind on the surface, this electron cannot flow easily. So you will get then higher impedance. So this is the actually simple technology behind this impedance spectra. And no need to wash your surface because you don't have any secondary antibody here.
Got it, sir.
Okay.
Sir, can we control the amount of these numbers of electrons to be passing through this electrode, sir?
Yeah, you can use high concentration then.
Okay. So numbers,
iron,
particularly in numbers.
Yeah, you can use high concentration. Sometimes if you use too much electron, then you will not get much difference. Maybe 1,000 electrons you are getting from here, from see my cursor. So from bulk to surface, maybe 1,000 electron passing. When you drop 1 nanogram target, maybe only 10 electrons stopped. So 1,000 and 10 you cannot compare. Sometimes they become overlap to each other. But if you can control like 100 electron, and from the 100 electron, if 10 electrons stop, then you can measure easily. Vibhuti, clear now?
Okay, sir. We can say by looking at the Nyquist plots on the semicircular curve. So this much of amount of electrons are present.
Yeah. Sometimes they can be overlap to each other because number of the electron difference is very low actually.
Okay, sir. Okay, got it, sir.
Good. Very good discussion today. So any more questions? Otherwise we can stop today. Maybe Monday also again I will discuss. We need this kind of discussion. Then only it will be clear. Then we'll go to the next topic. So we'll have exam Wednesday. So Monday we'll discuss again. I will teach you some more thing that I didn't cover. Here I given the question I told you, like some basic principle of wash free bioscience. These things I will teach you some part on Monday. Then we'll take exam on Wednesday. Okay.
Monday class would be.
Okay, sir.
So Wednesday we'll have exam from 3 to 4.
Sir?
Yeah, tell me.
Sir, Monday class would be included in the test or not?
No, Monday will be only discussion. Just washing free, I will elaborate a little more.
Okay, sir. Okay.
Okay, then good. Thank you guys. So we'll see you on Monday.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Wait 1 minute,
Thank
right?
you, Thank you, sir.
I will take the attendance. Download the attendance. Yeah. Okay. See you guys. Bye.
Hello.
Brotin, hello.
Hello,
Hello.
sir.
Yeah.
So can you hear me?
Yeah, I can hear you.
So in case of EIS, if we are using EDC NHS system, and mainly sulfur NHS has very high leaving aptitude, that's why we use. But if the sulfur NHS doesn't leave, then the RCT value will keep on increasing. So how can we be sure that sulfur NHS has been leave or not?
Sulfur NHS. See, we are in the impedance case, nothing. See, we are sulfur NHS means the primary antibody already coated, right? Your surface that should be stable. Then this surface, see here, I'm showing. See, so this sulfur NHS, when in this case thiol, but sulfur NHS, when this will be provided to the user, right? This should be stable. Then you are adding the target concentration here. If more target bind, then electron transportation from solution to surface will be hampered, right?
So I'm asking, the primary antibody has perfectly been bind or not? How can we sure?
That one. So that one we have to check some different way. That the stability. Then in this case, you have to check some different way. How we can check this means primary antibody is stable or not. In this case, maybe you can check by impedance measurement. Okay, so like you have the 100 antibody on the surface, you will get one impedance. Then again, then you can done some one experiment with by using maybe one target concentration like 1 nanogram. Suppose you have to keep constant. Maybe then after 1 hour, maybe after one day, you check same experiment. So if you not get the similar result, if it is decreasing, it means maybe your antibody not stable. They are actually decaying from the surface, right? So somehow you have to fix the concentration. You have to check the impedance some time interval.
Okay, sir.
You
I
can
was
add
asking.
So this is one experiment.
During the immobilization of the primary antibody on the electrode surface, if we are using EDC NHS, and if the NHS means those aromatic group with sulfate, that thing remains on the surface and doesn't leave, then also it is electrically not very conductive. Then also the RCT value will increase.
Oh, you are asking that one. Okay, good, Perkin. So that is also very good thing. So if this you got something like this, so what will happen? You have to use some other like BSA you are using, right? So that that is not leave. They can bind with the BSA, and that part will be deactivated then.
Sir, can you please repeat one?
I mean, if your this NHS part, if it is there in this, I don't know. Yeah, it is there. Right here, right? This part, this one, or this one?
No, sir. The next slide.
This one.
Yes, sir. This one.
See,
so
if it is
10th slide. Slide number 10.
Slide number 10. This one, right? This aromatic part. You are saying this one.
Yes, sir.
So amine group binding with this side, right? So see, if your primary antibody, if this part is remain after binding antibody, some part maybe remain, right, on the surface.
Yes.
So, see, when you are using washing buffer, that contain BSA, right? So BSA also protein, and it has some free amine group. It has some free amine group. So that can bind with this, and it can deactivate this one.
Oh, okay, sir.
Yeah, so that's why BSA helping many way. It can that way also it can deactivating the non-specific binding.
Okay, sir. Okay, thank you, sir.
Okay, good question. So similar way we will discuss. You can list some questions on Monday. Again, we will discuss. Huh?
Okay, sir.
Okay, thank you guys. Thank you.
Thank you, sir.